So I'm going to begin by talking about calculus. In fact, to a large degree, this talk is about shifting your point of view about calculus and how that might affect the way you think about physics, which of course you always frame in terms of calculus. So let's begin by talking about dx, dy, and dz. Now, I'm going to assume that dx, dy, and dz are nilpotent. This is not necessarily in the same theme as Peter's nilpotence, but nilpotence nonetheless. And the intuitive idea for having dx squared equal to 0 is that it's so small that when you multiply it by itself, it just disappears from sight. And we're going to assume that any infinitesimal whatsoever has square 0. So if you took a linear combination pointing off in some other direction in the little Cartesian space there, that should also square to 0. But let me just dwell on that in a moment. Let's see how we do calculus. You want to find out what happens when you displace x by dx and square it. Well, in this calculus, you have x squared, you have 2x dx, and you have dx squared, but dx squared is 0. So you get x squared plus 2x dx. And so you see that the difference between x plus dx squared and x squared is 2x dx. And then that tells you that the rate of change of x squared with respect to dx is 2x. And we have found the derivative of x squared. You can continue on in this fashion and do all your calculus, or nearly all of it, using nilpotent infinitesimals. I leave it to you to develop a little more of that if you haven't seen it before. But now, what is the consequence that dx plus dy squared should be 0? Well, multiply it out. And you get dx squared, and you get dx dy, but you also get dy dx, and you get dy squared. And the two ends are both zeros, so you get that 0 is equal to dx dy plus dy dx. And so dx dy is minus dy dx. And this is called differential forms, or Grossman algebra, in the course of its historical development. This is the right thing to do. This is the non-commutativity that lies at the bottom of the calculus and gave people a lot of trouble to justify in the usual way of developing calculus, so that you won't find it until you're studying advanced calculus in many variables. But non-commutativity is down there in the base of the calculus. And you might try to find an intuition for why a little displacement in x multiplied by a little displacement in y should be anti-commutative. And it isn't so far to find it, because if you think that it means a bit of area with an orientation associated with it, why then the minus sign makes sense, because if you multiplied in the other order, the orientation would shift. In any case, this is the footprint of a standard technique called differential forms, where one works with the non-commutativity in exactly this way. Nothing radical about it, but I think it's a little radical to realize how elementary it is. Then there's discrete calculus. As I said, we're talking about forms of calculus. Discrete calculus was developed by George Boole, and he wrote a book about it. And it's not usually taught, but it's a very useful form of calculus. Here I'm going to have my step size 1, so I don't divide by a step size. And the derivative of f is just f at n plus 1 minus f of n. We're evaluating natural numbers. And if you don't mind, I will define f hat of n to be f at n plus 1. All right. And then you will find that you have a nice formula for the derivative of a product. The derivative of a product is given by the derivative of the first guy times the second, plus f hat times the derivative of the second. You need a little shift in there, a little shift that wouldn't happen if you were doing infinitesimal calculus, because the step size would be infinitesimal and there wouldn't be any perceptible difference between n and n plus 1. An example, if we had f of n as n squared and g of n as n, then fg is n cubed. We can find the derivative of n cubed. That's n plus 1 cubed minus n cubed. And you get 3n squared plus 3n plus 1. To take the derivative of n squared, you get 2n plus 1. Take the derivative of n, you get 1. And you'll see that it works out. But what can we do with this? Well, for one thing, it's very useful. Discrete calculus is incredibly useful. You need, if you want to do an exercise or two with it, I give you an exercise to work. Define x upper n to be this product, which is the analog for discrete calculators of x raised to the nth power, x times x minus 1, and keep on going on down that many terms. So for example, x upper 2 is x times x minus 1. And then you will find that the derivative of x to the n is n times x to the n minus 1, as it was usually in calculus, but you need this shifted gadget. And then here's an exercise. Suppose you had f of n and you wanted to find out a formula for it, f of n being the sum of the squares. Well, look at the derivative of that. The derivative of that is the sum all the way up to n plus 1 squared minus the sum all the way up to n squared. So it's just n plus 1 squared, which is n squared plus 2n plus 1. And I can write that in terms of my x upper n's. It's n upper 2, 3, n upper 1, n upper 0 by just rewriting it a little bit. And now we can integrate because we know that the derivative of 1/3 n upper 3 is n upper 2, and the derivative of 3/2 n upper 2 is 3n upper 1, and the derivative of n upper 1 is n upper 0. And then you can check that I got the endpoint evaluation right, and that's a formula for the sum of the first n squares, just automatically by doing calculus, just like one does many things in calculus. Very, very useful kind of calculus for discrete problems. But what I want to observe about discrete calculus is that it's also related to non-commutativity. And the way to see that is to introduce a shifting operator, which deals with the fact that we want to look at f of n, but we also want to look at f of n plus 1. And remember, f of n plus 1 is f hat. So I'm going to introduce a shifting operator j, so that fj is equal to j f hat. If you push it past f, it turns it into f hat. And then I'm going to define a brand new derivative by multiplying on the left by j. And watch what happens to this derivative. Nabla, I'll call it. Nabla of f is j df, which is j times f hat minus f. Remember, the derivative of f is f hat minus f of n plus 1 minus f of n. So we have jf hat minus jf. But jf hat is fj. And now you're looking at a commutator. You're looking at the difference between the evaluation of fj in that order and the evaluation of jf in that order, the commutator. And we see that Nabla of f, this new version of the derivative, is a commutator. So we can express derivatives in terms of commutators, in terms of the difference between doing something in one order and doing something in the other order. Orders happen all over in real life, of course. For example, I may pour a cup of I may choose a cup and then pour a cup of coffee. And if I do it in that order, you get a certain result. But if I pour the cup of coffee and then choose the cup, you get quite a different result. And you can check that the Nabla applied to FG does satisfy Leibniz's rule that nabla of fg is nabla applied to f times g plus f times nabla of g. I'm interested in that because I like my calculi to look like infinitesimal calculus, even if they aren't, because it's easier to calculate. And the proof of this? Well, here's our basic rule about D. And if we apply nabla, then we multiply by J. And now watch this. It's kind of fun. So D of FG we know is DFG plus F hat DG. And I multiply by J. So I get JDF over here. But here I get FJ DG because JF hat is FJ. When you push J past it, it shifts it. And JD is nabla, and JD is nabla, and there's our rule. So that is showing us that when you have a derivative defined by a commutator, it does satisfy Leibniz's rule. Now, that was a little calculus lesson, and we're going to come back to discrete calculus and commutators in a moment. But the motivation for, one of the motivations for thinking about this was a paper by Dyson about a derivation that he learned from Feynman about getting electromagnetism out of commutators, as though one was getting electromagnetism out of quantum mechanics, because quantum mechanics is often expressed in terms of commutators. We'll come back to that theme in a moment. But this is the way it looked to Feynman and Dyson. One had coordinate directions, x1, x2, and x3 positions. And it's given that they commute with one another. That's what this little symbolism means here. So I have ordinary coordinates that commute with one another. And then I have x dot, which is given to me, which is the time derivative of the coordinates. In other words, the velocity vector. And I look at the cross product of the velocity vector with itself. And the reason that that isn't zero, because we usually think that cross products with themselves would be zero, is because it isn't given that the velocities commute with positions. This is analogous to quantum mechanics, where the position does not commute with the momentum. And here it is going to be assumed, rather analogous to quantum mechanics, that at delta ij's, that means that xi commutator xi dot is zero, but xi commutator xj dot, I'm sorry, is one. But if j is different from I, it'll be zero. And then the acceleration, the second dot, is decomposed into a field E and the cross product of x dot with h. And this defines E and h, and Feynman-Dyson proved that E and H satisfy Maxwell's equations. That is, that E and H actually commute with the xi, that the divergence of H is zero, and that the derivative of H is given by the curl of E, given in terms of the curl of E. And this is a long ago time. Pierre and I were talking, and he wanted to know whether we could give this a discrete interpretation. Might there be some way to interpret this discretely? Could we do it in terms of bit strings? What can we do with this? This is what Feynman's, what the Dyson paper looks like. And this is the reference to the paper that we eventually wrote about this. And we did interpret it discretely. And the way we interpreted it discretely was by understanding that derivatives defined in terms of commutators can be regarded as discrete calculus, as I just was telling you about, as though it were only a calculus lesson. But we'll come back to it because there is the question of time, which we haven't mentioned yet, and time is of essence. So I want to still talk about some history. In the 1920s, Hermann Weyl had the insight that electromagnetism came from the properties of a line element in space-time. And he had the idea that you could get a unified field theory at that time which would unify gravity and electromagnetism. There not being other field theories prominent at that time. And he worked out a unified field theory, which occurs in his book, Space-Time Matter. And you can read it. It came under some criticism by Einstein, which Weil eventually understood he had to accept. But on the other hand, it turned out that the theory, if you reinterpreted it in terms of quantum mechanics, made fantastic sense. And it became what people call gauge theories these days. Now, I want to show you what I think is the essence of this. Here's a differential one form. And I'm going to deal with these things by differentiating them in the nilpotent calculus so that dx, or the Grossman algebra, so that dx dy is minus dy dx. And I'm going to differentiate this. This is the line element. This is a Hermann-Weil line element. And we're going to differentiate it. And if we differentiate it, that means we differentiate the f with respect to x, with respect to y, with respect to z. And when you do that, you get df, which is the derivative of f with respect to x times dx, plus dy, df plus the derivative of f with respect to y times dy, plus the derivative of f with respect to z times dz, the total differential of each of these, and multiply everybody out. And that means you're going to have in the resulting expression dx dy's, dx dz's, dy dx's, dx dt's, and so on. But when you add a dy dx, you change the sign and pull it back over here. So you see that's what's happening, getting these differences here times a dx dy in standard order, and so on down the line, and things with time as well. And we get two rows of things in the differential. One are differences with respect to space, and the others are differences that involve time derivatives of these guys here. And what Weil realized was the following, that if he looked at that, he could understand that what he had computed here was the curl of the vector FGH. And that he could understand that what he had computed over here was, of course, simpler. It's the derivative of this phi with respect to space, the gradient, and the time derivative of these guys here. So that if you were to take FGH and call it the vector potential, a standard term, and you were to call phi the scalar potential, then you have that d lambda is giving you the curl of A, the vector potential, and the other part is giving you the negative gradient of phi and the negative derivative of A with respect to t. And those are the correct formulas for the E and the B field from a vector potential and a scalar potential. So Weil realized that if he took the derivative of the differential form, thinking in terms of Grossman algebra, then the electromagnetic field appears in the derivative. That's his fundamental insight, that taking the derivative of that differential form gives you the electromagnetic field. If you take two derivatives of a differential form, d squared, you get 0. And those coefficient equations are Maxwell's equations. Maybe I put it in the next slide. No, it didn't bother with. That's how you get to Maxwell's equations, by differentiating it one more time. And and so then Weil had the notion that what the electromagnetic field was about. If the electromagnetic field is not 0, that would mean that that what would happen is that this lambda, if you were to integrate along it, would give you different results depending on what path you took. It is the independence of path for integration along lambda that corresponds to the vanishing of the field, of the vanishing of D. If lambda is itself a derivative, then it'll be path independent. So he understood that what the electromagnetic field was actually about was the way things would vary if you went along one path or another path for this differential form. And he wanted to put it directly into the geometry. And Einstein criticized this by saying that, well, things like spectral lines depend on very precise determinations of lengths. And if there were this kind of variance due to the electromagnetic field, then our observations are not showing it. But nevertheless, a very persistent idea and a very beautiful observation about where the formalism of the electromagnetic field comes from. So as I said, if you compute d squared lambda, the coefficients are del dot b and del cross e plus db dt. That's fun to do, and I won't go doing it here. And then if it wasn't zero, then you would have del dot e, you would have some other coefficients. And as for the other two Maxwell equations, they correspond to charge and current, and you have some extra terms. So in a certain sense, all of electromagnetism is coming out of differentiating this line. And then somehow the changes of lengths of lines or the difference between paths going along different paths is deeply related to electromagnetism. The theory didn't quite work, as I said, as a direct extension of relativity. But then, I think you don't need to see this slide, it's just what I was saying. But then many years later, in the 50s, I guess, or the late 40s, Aharonov and Bohm discovered that, and in the in-between, people realized that integrating the potential along a path and finding that could conceivably give different results for different paths could be shifted to a phase of the wave function. You could instead of thinking of this integral, you could think of e to the I times that, and it would correspond to a phase shift in the wave function. And that became the theoretical interpretation that persisted for Weil's idea and became gauge theory. But Aharonov and Bohm found an actual experimental result exactly related to this, where you could have an electromagnetic potential but no direct field, and you would detect differences in the interference pattern in a quantum mechanical experiment due to the electromagnetic potential. So that, in a certain sense, Weil's idea is precisely right, that those paths are, that integrating along a path will indicate the presence of the electromagnetic field, but the place where it becomes detectable in the physics is in phase and interference at the quantum level. So it's still very mysterious and beautiful situation. As I said, this got generalized. The way it gets generalized is you start with a one form, like I did here, and you allow due to Yang and Mills primarily, you could let the one form have matrix values in it, so that the non-commutativity comes in another way with the matrices. And then the field, remember, was the differential of the one form. So in this case, the differential of this form has to involve the way the A's behave with regard to one another as well. So instead of just having the differential, you also need, it turns out, to do this kind of theory, the products of the A's with themselves and the way they are commuting and non-commuting with one another, which can be expressed this way. So the field gets generalized in that fashion. And at the level of what we're going to do, we're going to look at a situation, and we're going to see that it corresponds exactly to this, where I see I jumped ahead a little bit in formalism, but I want you to look at this. In the original physics of gauge field theory and so on, what one did was one generalized the derivative. And one generalizes the derivative to a covariant derivative where the A is placed along with the I. And what I'm talking about here is the idea that you are going to think of the A as corresponding to a parallel translation, as you do in differential geometry. And I don't have the feedback to tell. Maybe I should stop the view so I can, no, I don't get a feedback of my own image, but I think I'll just stand back and you can probably see what I have in mind. What I wanted to remind you about is what happens in differential geometry, where you can think of, for example, a vector which is on the surface of a sphere, and my thumb is on the surface of the sphere whose center is my body. And when I move it around, I'm moving the thumb in parallel to itself, keeping it pointing in the same direction as I move it around the surface of the sphere. So you might think that if you took it around a path, like over here, and then up to the North Pole, and back down to where I started, you would think that it, or if you took it all the way around the path, it would come back to where it started, but it didn't. I started here with my thumb pointing up, and I went around the equator, and then I brought my thumb all the way up to the North Pole, and I'm moving it parallel to itself all the way, and then back down to the equator, and it's changed its direction radically. Even if I went around a very small circle, it would change a little bit, and we could examine how much it infinitesimally changed. So one can talk about differences that are combined with some form of parallel translation. Because why did it happen? Why did it happen that we had this kind of differencing in the differential geometry of the sphere? It had to do with the fact that the inhabitant of the sphere imagines that there's no change in that vector. But if you were to stand outside, you would see that the vector is changing, but it's changing in a way that is not seen by someone who's projected into the surface of the sphere. And you need a function which describes how that change is occurring, and that function is the AI. And the field, the electromagnetic field from this point of view, is coming from these changes in parallel translation. And as I said, all that picture became quite accepted in physics at the level of formulating electromagnetism in terms of quantum theory and letting the parallel shifting have to do with the phases of the wave function. If you then were to go back to your calculus and figure out the commutator between delta I and delta J, that would correspond to the difference between two paths. One path where you moved in the I direction and then the J direction, minus the other path where you moved in the J direction and then the I direction. And you would be going around a parallelogram here, 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 and back to where you started. And you calculate that and you find that you get the value of the field. If it were only electromagnetism, it would be dIAJ minus dJAI. So that's a picture of the way this physics looks and the way it got generalized. Excuse me, I want to go back to my viewer here. You don't need to see this. This is what I was describing in words. But it isn't just the infinitesimal transport around a curve that turned out to be of great interest in recent years, meaning recent years like 40 years. Witten back in the 1980s said, look, let's take one of those one forms in 3 space and let's look at what happens when you go around a path and come back to where you started and measure that. And the path could be knotted. And then it turns out that the knottedness of the path is really significant for what happens when you go all the way around. So that phase which can be measured by taking the trace of some matrix phase, that phase turns out to really reflect within it topological properties of the knot, along with some other things about the curvature, and they have to be integrated out. So you need to integrate over fields, over different connections, over different potentials in an appropriate way, and extract out of it topological information about the knot, so that an entire revolution in knot theory and its relationship with physics occurred still as a result of Hermann Weyl's ideas and these non-commutativities that are present. So now, I'm watching how much time we have. We have about 20 minutes, is that right?
Yeah, that's right.
Okay, so what I want to do is to back up from these kind of specifics and talk about non-commutativity as generally as I can. So what's that going to look like? Well, first of all, let's be a little more specific about time. If we're doing time discrete derivatives, then what does that mean? That means that we have a series of positions, x, x prime, x double prime, and so on. And the time derivative would be the position at the next time minus the position at the present time divided by the change in time, dx dt, where dt could be finite time increment now, not necessarily infinitesimal. And I want to think about what happens when I make observations. I could observe the velocity, that's the x dot, and then I could observe x. Or I could observe x and then I could observe the velocity. But thinking discretely, these are quite different. If I observe the velocity, I have to let the clock tick, because I have to find out where x is at the next time and take the difference and divide by the time. So when I observe the velocity and then observe x, I'm getting x at the very least at the next time. So I've written that here. Here's the velocity computation, and here's the position evaluation at the next time. On the other hand, if I observe x, I imagine that it doesn't take me much time to observe x. And so when I observe the velocity, I'm still working from the base of x at that time and letting the clock tick. So you see, they're different. One evaluates x and then evaluates the difference. The first evaluates the difference and then evaluates the x at the next time. And if you made the commutator there, x position times velocity minus velocity times position, you get the square of the space step, x prime minus x, divided by the time. So you have a commutator equation. And these commutators are clearly very important for thinking about the physics if you think about it discretely. And they will be ignored utterly if you're doing it in an infinitesimal analysis of the physics, because there won't be these changes and you won't have the notion of xx dot being different from x dot x. So we have that if we took xx dot equal to a constant, then the change in x squared divided by the change in time would be that constant. And then you could think of a solution to that where the new x is x plus or minus that step. And this is a discrete analog of Heisenberg's equation. And the solution I'm suggesting to you is a Brownian walk, a random walk. And the diffusion constant for that walk is, by definition, the square of the length of the step length divided by the time interval. And the reason for the diffusion constant being important has to do with differential approximations to a differential equation for the Brownian walk, which I don't want to go into, but the differential equation has the diffusion constant in it. You think of the length of the walk getting very, very small, but the length of the time also getting very, very small, but in such a way that the square of the length divided by the time is held constant. And then you can think of very, very infinitesimal sort of walks that have that property, and they can be regarded as satisfying a regular differential equation called the diffusion equation. So this fits in. This is a way in which the discrete physics fits in with continuum physics. Now, as we said before, the discrete calculus is embedded in commutator calculus, but now our shift operator is interpreted temporally. I'm going to put the shift operator on the left of x, and when it shifts over to the right, x goes up by 1 tick. So then, if I were to redefine the derivative by jx prime minus x divided by dt, as we did before, then we get that x dot is a commutator. We get that x dot is equal to the commutator of x with j over dt, the change in time. And that satisfies the Leibniz rule. And we can analyze all of these things in a discrete calculus that's non-commutative like that. And then I'm going to jump from things we could do with that to generalizing it as largely as we could. So we're going to work in some algebra where I can take commutators. As general an algebra in which you can take commutators as you would like. And I can define lots of derivatives by choosing an element n in my algebra and defining noblesse of n of f is the commutator of f with n, fn minus nf. And then that will satisfy Leibniz rule, and we have calculate, lots of calculus, lots of derivatives, and they don't commute with one another very much in general. But there is a key thing about algebras of the kind that I'm working with. Algebras of the kind that I'm working with where things don't commute, but addition is commutative and multiplication is associative. I'm not doing non-associative algebra here. Then you have a very pretty cyclic identity about commutators called the Jacobian identity, which comes up again and again and again. So you have the commutator of A with B with C, and then you cycle it, putting C at the beginning and then putting B at the beginning and add them up, and it comes out 0. A nice exercise for you. But this Jacobian identity governs everything that goes on in this realm. And in particular, you can use it to check the following. Suppose you have two noblas, one represented by taking the commutator with ni, and another one represented by taking the commutator with nj. And you want curvature, and as I said, I think of curvature in the abstract as the commutator of the operators. Do an operator, do another operator, take the difference. Then you've come back to where you started in pathwise speaking, and maybe it's different. Well, then you get a very nice algebra formula that the commutator of delta I with delta j is actually equal to a commutator with the guys that represent them, ni and nj. So we can think of the commutator of ni and nj as the curvature related to delta I and delta j. And so that's just what it looks like to verify it by using the Jacobian identity, better done offline. So we can think of a world in which we have a lot of these, and I may use ordinary notations like this. The derivative of f with respect to the a direction is noblesse of a, is the commutator with respect to a. And then the curvature tensor, generalized, the curvature between two of these is the commutator of the guys that represent them. If the guys that represent them commute, then the curvatures, then the operators commute, and it's flat. So now we're in a position, this is elementary but very non-commutative. We're in a position, oh, I'm going to skip this. There's a very pretty identity about curvatures called the Bianchi identity, which is often used, and it's just the Jacobian identity rewritten in terms of curvatures. You see what I did? Here's the Jacobian identity for NA, NB, and NC. But if you thought of this as RAB, then this is RAB, take its derivative in the C direction. This is RCA, take its derivative in the B direction, and so on. And this adds up to 0. This is a famous identity in differential geometry. but in our context, it's just the Jacobi. We have non-commutative worlds, but now we want to go back to doing the simplest calculus we can, and then use it as a reference point as we do. So the simplest calculus would be a place where the coordinates all commute with one another, and the guys that represent the derivatives all commute with one another, so that the derivatives commute with one another. So I have the derivative of f with respect to xi is going to be, by definition, the commutator with pi. And there is a dual notion of the derivative with respect to pi being xi commutator f. And we want that these derivatives commute, so the world is flat. And we're going to assume that the derivative of xi with respect to xj is delta ij. It's 1 if I equals j and 0 otherwise. And now this looks just like the beginning of the Feynman-Dyson, right? This is a flat world in which everybody behaves nicely. But from the point of view of an imaginary course in the calculus that began in a non-commutative way, this would be just setting up Cartesian coordinates. But then there's time, and as we've seen, time should be represented by the commutator with somebody called h. And in quantum mechanics, you need an I, but we're not dealing with that here. So this is a flat world, and we have we might as well call h our Hamiltonian. And then, in fact, we have Hamilton's equations as a tautology. Now, the tautology I'm just going to prove for you here, and then I'll make a remark. But suppose I wanted the derivative of pi with respect to t. That's the commutator of pi with h. But that's minus, because when you switch the order, you change the sign of the commutator. That's minus h commutator pi, but by definition, that's minus the derivative of h with respect to xi by our definition. And what about the xi dt? Well, that's xi commutator h, and that's equal to the derivative of h with respect to pi, because that was our duality here. Xi pj is delta ij, and we can think of taking the commutator with xi as being, by definition, the derivative with respect to pi. And then we have, as you see, that the derivative of the momentum with respect to time is equal to minus the partial of the Hamiltonian with respect to position, and the derivative of position with respect to time is equal to the partial of the Hamiltonian with respect to the momentum. And those are called Hamilton's equations. And these are just a tautology in this world. But where did Hamilton get them? Let me remind you, because then it will look a little more mysterious to you. Hamilton's equations, the momentum in a very elementary physical world, quantum classical mechanical world, the momentum is mass times dq dt. Q is position. Mass times velocity. The Hamiltonian is the energy. It is p squared over 2m, that's 1/2 mv squared, plus a potential v of q. And Newton's law says that ma, md squared q dt squared, is equal to minus the derivative of the potential. So then we calculate, and we find the h dp, that's equal to p over m. The h dp, you go back up here and differentiate it with respect to p, and you get 2p over 2m, you get p over m, and that's dq dt. So the h dp is dq dt. And what about the h dq? Well, that's dv dq. Again, from this. And that's minus md squared q dt squared, which is minus dp dt from Newton's law. And so we have it. dq dh, dh dq is minus p dot, and dh dp is q dot. That's Hamilton's equations, and that's the situation through which Hamilton was getting these equations. He wasn't working in the non-commutative world, but he invented the non-commutative world because, you see, Hamilton went further and he said F dot. F dot is the FDT, but the FDT is the FDQ times Q dot plus the FDP times P dot, which is just the total differential in the advanced calculus. The rate of change with respect to one variable times the rate of change of that variable plus the rate of change with respect to the other variable times that variable. But we know that the FDQ is, then we know the Q dot is the HDP, and we know that P dot is minus the HDQ. And so Hamilton understood that he had a beautiful formula here. He had proved that F dot is equal to the Poisson bracket of F with H, where the Poisson bracket of A and B is by definition this differential equation form, dA dQ times the BdP minus the AdP times the BdQ, changing the order of whether you differentiate with respect to P or with respect to Q. And it turns out that brackets, Poisson brackets, behave like commutators. They satisfy the Jacobian identity, and Hamilton reformulated classical mechanics in terms of a non-commutative world where the non-commutative world was built in Poisson brackets, not in commutators. But then the fantastic thing, which we aren't talking about in this talk, is Dirac's insight many, many years later, way off in the 20th century, that if you wrote an IH bar in front of that bracket and replaced it by a commutator, you transferred from classical mechanics to quantum mechanics. That quantum mechanics involved taking the Poisson brackets and replacing them by commutators. So you went from one non-commutative world to another in the transition to quantum mechanics. So what we're trying to do is look at the form of all of this by stepping back a couple of steps and also thinking of the commutators as being representative of the discrete. I'll skip this slide. Now, what about general equations of motion? I think we're verging on the end here, but you're coming near the end here in a place to stop anyway. If I want to talk about general equations of motion, then I have some coordinates xi, and I would say that dxi dt is equal to, well, on the one hand, it's the commutator of xi with the Hamiltonian. On the other hand, there's somebody in my big algebra that describes it, because my big algebra contains these functions of time and space. And I'm going to write that GI with malice aforethought as a difference between the basic momentum and the AI, some AI that represents the difference. So AI is by definition the difference between PI and GI. And then you could ask, well, what's the curvature associated with derivatives made by GI and GJ? And you compute, and there it is. There's the formula for the gauge derivative. There's the formula for the gauge field and the generalization of electromagnetism. So you see all these things, if you take this non-commutative viewpoint, which has been pointed at in so many directions, and step back and just write in that viewpoint, all these things come out as kind of tautologies that have to be there. And we can wonder, well, what AIs should we choose? And as you know, Hermann Weyl let AI be zero. Later, Yang and Mills had very interesting and complex AIs that correspond to the Yang-Mills models. And the AIs can even be chosen to do topological work. What about metrics? Just a couple of words about metrics. I say that I should take the metric. I want to explain why I should think of the metric as having this formula. So I want to think about the metric in the classical case. The metric in the classical case is ds squared, the distance squared. And it would be gij times dxi dxj, sum over the different choices there. But then you get ds squared dt squared, acceleration of that. That's equal to dividing by dt twice, and that's pi pj. So you see, this corresponds to energy. And so it would be natural to take the Hamiltonian to be 1/2 Gij pi pj in the classical case. And then in the non-commutative case, I may have to consider orders and rewrite my Hamiltonian and start with some metric coefficients that I hope would be commuting things to begin with and symmetrical. And then you can calculate that the Gij is going to be a certain commutator. So we're running out of time, so I don't want to actually do that calculation, but it's not hard to see that if you choose a quadratic Hamiltonian, then the metric and everything are working nicely, and you will get this. And the derivation is a little bit of algebra with the Jacobian identity again, which you don't want to look at. But then furthermore, if you have a quadratic Hamiltonian, then you find that there's a nice harmony between the time derivative and the advanced calculus time derivative, which says that the derivative of f should be equal to the derivatives of the coordinates multiplied by the derivatives of the function with respect to their coordinates, that this should work out. And it really has to be quadratic Hamiltonian in order to work out. So one can fit the non-commutative world together in that way with a quadratic Hamiltonian and continue the investigation. So just to summarize one little extra bit, one gets things that are very close to differential geometry if one keeps digging. You can use this understanding of the metric to find that you get what's called the Levi-Civita connection, which describes the particle moving it describes the geodesics that it moves through. It describes the differential geometry in terms of the derivatives of the potential. But these derivatives are commuting with one another, and you get a non-commutative Levi-Civita connection. And one might wonder, where did that come up, if it came up at all in the other worlds of people's calculations? And one way to see it even in Hermann Weyl's original work is to look at a symmetrization formula, which shows you that the connection appropriately added to itself will give you just a derivative of the metric, and that derivative is a covariant derivative of the metric with respect to the gauge. And this goes straight back to gauge field theory and Hermann Weyl. So there are lots and lots of comparisons that one can make between this abstract point of view, which has the peculiar property of leading you directly to formulas that people work very hard to get from within. And there are many questions about the relationships between this and relativity and quantizing gravity and other things. Quantum gravity theories, like the ones due to Ashtekar, are based on making gauge theories that are related to quantum gravity. And I think that some of them will fit into this context as well. There are lots of things to think about here. I'm going to stop at this point. Thank you for listening.
Thank you very much, Lou. As usual, a great sweep across all sorts of things and clearly explained. Who would like to raise his hand? John Williamson, would you demute? Did you unmute yourself? John, unmute.
Yes, there we go.
There you go.
Thanks, Lou. It's always a pleasure listening to you. Always learn something new. Question though, you're talking about the phase change that you get by virtue of a particular kind of knot. So, and taking out the geometric phase that has to do with going around that these things had characteristic phase changes that were dependent on the knot. What kind of phase changes do you get in systems? Are they integral? Are they sort of pi by 2, pi by 4 crossing, or what sort of numbers do you get out for those phase changes?
Well, first of all, they individually they're not invariants of the knot, because if you if you change the curve of the knot by a small amount, then going around a little tiny path will calculate the curvature of the gauge field. Will give you the field. So that's why you have to integrate.
Okay,
but then it's true that there are also large scale periodicities. So things have to be defined at certain roots of unity in order to make it well defined.
Okay, so these are roots of unity. So it's like a phase change, like an e to the I theta phase change that you get, and you have a theta there, but that theta is not integral or quarter integral or half integral or anything like that. It's something which, because I suppose if you take the curvature and make it very, very large or vary the curvature, is there an asymptotic value that these things go to if you make the curvature essentially zero or concentrate?
Well, when you integrate over the fields, you're washing out the local curvature behavior, and you're just getting a residue of what's topological.
But that topological residue isn't characterizable by a number. It could be any phase between 0 and 2 pi.
You can normalize so it's actually characterized by some number, yes.
But that number's not a logical number like pi by 2 for one crossing or pi for 2 crossings and so forth. It doesn't work like that.
Well, it's not just counting the number of crossings. No, it's something subtler than that.
Okay, fair enough.
And it is related to, in some cases, related to very old invariants of knots and links, like the number of times that one curve goes around the other. But if you wanted to try to understand what does it actually mean, even say for a trefoil knot, it's kind of hard to tell what it means. There are combinatorial invariants that calculate the same thing in terms of diagrams, but we don't know what they mean either.
Okay.
Or and then there's another way of thinking about it, which is, no, I mean, I guess I should just stick with what we know, some formulas for them in terms of more familiar things. Gauss made the original breakthrough. Gauss said, oh, you can find the linking number between two curves. And what you should do, he said, is you should, you have two curves in space, and you take a point on one curve and a point on the other curve and draw a vector from one to the other. Yeah. Okay, and take the corresponding unit vector. And so now you have a unit vector moving on the surface of the two-sphere.
Yeah.
And then you examine the properties of that mapping, and you can use it to count. In other words, you have a product of the two circles that correspond to the link. A torus. So you have a torus mapping to a two-sphere, and you count how many times the torus is covering the two-sphere.
I see what you mean. So, but that in that way, so you're taking the geometric phase, which would be precisely pi by 4 or going around one quadrant. You surely could subtract that in your integral, and then you would get a characteristic number. I would have thought, but that's a naive thought.
So one of the earlier things that integral will compute for you is Gauss's linking number. And when you examine when you examine the innards of the integral, it actually is producing the same differential forms that Gauss used.
Okay, that's cool.
Yeah.
That's cool.
Okay, John. Okay. I believe Grenville wants to say something. Is that right? You need to unmute yourself. You've got a little hand up. There we go. Speak, Grenville.
Yeah, just thanks, Lou. No particular comments, but my mathematical, just thanks for your influence on my mathematical education. I seem to have grabbed stuff by osmosis, then 10 years later it appears in my own work. So thank you.
Yeah, one of the things I was saying about this is that it does this. We're looking for shifts of point of view here, and in this case, I think that there really is a shift in point of view about what mathematics should you be basing things on, right? Even if you look at calculus itself, well, then you have the option of thinking about things quite discretely or very continuously. And when you look at the models that we use, they aren't actually fixed to being one thing or another. It depends on how you view them.
Watch this space for the integration of discrete and continuous.
Right.
Barbara, you have
Yeah.
some statement
Sorry,
about what happens next.
yes, sorry.
Hope you're not
Always-
allergic to cats.
No. Allergic to many things, but not cats. Okay, we have a small change in the program. And if you look at your program, we should have had this sort of rather mysterious title by Sahu, 00000.